This video, we'll look at the first question on the 9.1.9.2 worksheet. This says to write out the first four terms of the given sequence. Is the sequence bounded? Is it monotonic? Okay, and so in the last video, I'd asked you to have a look at these before watching this video and checking your work. So what I'll do is just put the answers up for each one, and then we'll talk through them so you can check your answers. All right, so for part A, we got a sub n is n squared plus 3n. All right, so to write out the first four terms, right, these are 4, 10, 18, and 28. Those are found by just plugging in 1 for n, 2 for n, 3 for n, and 4 for n, respectively. All right, now this sequence is not bounded. Okay, why? Well, because I can make a sub n, which again is n squared plus 3n, as large as I like by making n sufficiently large. Okay, and so to bring up a graph here, I'm just using Desmos.com, the free online graphing calculator. I encourage you to check this out. I'm just putting in the function f of x, which is x squared plus 3x. And then as we discussed in the last video, right, I can plot the terms of the sequence. Here I have the first 5 terms, right, 1, f of 1, 2, f of 2, so on and so forth. So I get this visual representation of the first couple terms of the sequence. Right, they all fall on this nice quadratic function, right, this parabola. And I can see, okay, this is an increasing sequence, and the terms will grow without bound. Okay, so not bounded, and we are monotonic increasing. Okay, for part B, we got b sub n is 2 to the negative n times the cosine of pi n. So here's our answers for this problem. So as we noted, I think it was in the first video, cosine of pi n is really just acting as a sine alternator. Okay, so it's really just the same thing as -1 to the n power. And so for the first 4 terms, I have -1/2, +1/4, -1/8, +1/16. Okay, so here's a graph of that sequence, so -1/4, +1/8, -1/16, so on and so forth. They all fall on this dampened cosine wave. You can see the oscillations are decreasing in amplitude as we move to the right. And it's bounded, right, because all the terms of the sequence will be less than or equal to 1/2 in absolute value, right? They're all captured, all these green dots fall within this band from -1/2 to +1/2. So it's a bounded sequence. It's not monotonic. There's a note here, and that's because I increased from -1/2 to 1/4, but then I go back down to -1/8. Okay, so that alone tells us that this is not a monotonic sequence. All right, now c sub n, this is part C. We got 1 plus -1 to the n power, all divided by 2n plus 1. Okay, so for the first 4 terms, we have 0, 2/5, 0, and 2/9. Note here for the odd index terms, so C1, C3, C5, so on and so forth, those are all going to be 0 because I'm going to get 1 plus -1 to the n, which is really just going to be -1 when n is odd. I'm going to get 1 plus -1 is 0 upstairs. And so that's why those odd index terms are all 0. Now for even index terms, so C2, C4, so on and so forth, I'm going to get a 1 plus 1, which is 2 up top, and then I have the 2n plus 1 downstairs, so that's going to give me a 5, then a 9. It's going up by 4, right, from even index term to even index term. So the next one would be, 2/13, then 2/17, so on and so forth. So here's a picture of that sequence. So it goes from 0 up to 2/5, down to 0, 2/9, so on and so forth. So we can see here pretty clearly, right, it's bounded. In this case, all the terms are less than or equal to 2/5 in absolute value, and we're not monotonic, right? We increase and then decrease, and so we're not monotonic. All right, now for part D, you can see, I mentioned this earlier, we have this n with this exclamation point. That's what we call a factorial. And so before we tackle D, I want to just say a few things about factorials. So for a positive integer n, okay, we're going to define n factorial, which we write as n with this exclamation point, to be the product of all the integers from 1 up to n. Okay, so 1 times 2 times 3, all the way up until you get to n. So first couple, if we have 1 factorial, so n is 1 there, I just would get 1 for the resulting value. 2 factorial would be 1 times 2, which is 2. 3 factorial, 1 times 2 times 3 is 6. And so on and so forth, right? 4 factorial is 24. 5 factorial is 120. And so on, okay? Now, what about 0 factorial? Well, this doesn't really fit this mold, right? This definition really only makes sense if n is a positive integer. 0 factorial, by convention, though, is taken to also equal 1, okay, as 1 factorial is equal to 1. And there's various reasons why this convention is taken. If you're interested into exactly why, I'm more than happy to talk to you about this as well as other features of the factorial functions, interesting stuff. But for now, we'll just note that yes, 0 factorial is defined and it is taken to be 1. Okay, so on to D. First 4 terms, well, if n is 1, I'm going to get -1 to the negative first power, which is a -1. And then I'm going to get a 1 factorial over 4 to the 4th. Okay, so that simplifies to -1 over 256. If n is 2, I get -1 to the 0 power. That's a +1. And then I'm going to get a 2 factorial over 4 to the 5th. And that simplifies to 1 over 512, right? It's really 2 over 1024. So that simplifies. When n is 3, -3 factorial over 4 to the 6th, that is equal to -3 over 2048. The next term here, 4 factorial over 4 to the 7th, that simplifies a bit to a +3 over 2048. All right, so now if I graph this sequence, I can note here the vertical axis here. The scale is from -0.05 to +0.05. And I see there is some oscillation. Okay, so like the others, I've input the function rule. Notice Desmos does handle factorials. TI calculators don't have this programmed in, but Desmos does. And as I move from term to term, I'm seeing some fluctuation, and it seems like the fluctuation's getting a little more pronounced as we get closer to, like n is 10, but, we're still relatively small in magnitude for the size of the terms. Okay, so as far as whether or not this is a bounded sequence, at least from this viewpoint, it's not particularly clear. Okay, so now if I go ahead and zoom out a little bit, I can see that my next jump when n is 11 is down here. Still, again, it's -1 or -0.1487 blah blah blah. So, it's relatively a big jump, but still not very clear whether or not this is a bounded sequence. Now, if I keep going here, 12, 13, I can see it seems that the magnitude of the terms is growing. And if I zoom out here, I'm going to make the y value take on, say, a range from -50 to 50. Okay, I can see that, yeah, there's definitely more fluctuation. Now I'm down here at -19. Okay, so it seems that that fluctuation is becoming even more pronounced. Then it goes to 76, -323. So if I zoom, say, way out here, do -50,000 to 50,000. Okay, where am I at? Well, this is when n is 17, 18, 19, 20. And notice the value there is 34,573. Seems like that oscillation is becoming really wild, okay, as I move out further and further to the right, okay. And while this is not a proof by just playing around with this graph, it does suggest that this is an unbounded sequence, and it turns out that that is the case. Okay, so this term n factorial over 4 to the n plus 3, this thing does approach infinity as we let n approach infinity. This is not a terribly obvious statement that this numerator does blow up. It does take a while. Again, looking at just the first couple terms does not make that that fact evident. But we will, when we actually talk about limits in more detail, be able to show this. Okay, so this is not a bounded sequence, and it's definitely not monotonic, right? Because of the sign alternation in particular, be increased from -1 over 256 up to +1 over 512, and then back to negative. So it's not monotonic. All right, cool. Well, that's gonna do it for this video. I will see you next time. Thank you.